This week's topic is optimization, and particularly optimization as it applies to engineering design. So when we define engineering design, it don't always have to be designing a part or a device. Certainly it can be designing processes, systems, etc. But what separates engineering design from other types of design is that you do apply principles from science and math there. And this last statement here is optimal in some respect. In other words, you're trying to come up with the best design. So what makes it the best? What makes it optimal? Well, you have some objective measure that makes it such. For example, that if it's a part that's got to fly on an airplane, it might be that it's the lightest weight. If there are things you're going to sell a million of, maybe you have to make it the least expensive. And you can see all those other examples there as well. But in some way, we want to define what makes this the best design. So let's look at an example. So we're suppose that you need to design a beam. It's going to be 10 feet long, and you're going to put 500 pounds weight on the end. And when you apply this 500 pounds, the bar is going to sag a little bit at the end. And another thing that you've decided here is that you can't let that deflection be more than 1 inch. Okay? So with that in mind, we have some preliminary design decisions we have to make. We're going to make it out of steel, we're going to make it out of wood. What shape do we want? So we might decide up front we want to use a cylindrical bar, circular cross section. It can be hollow, but nice thing about that is that no matter how we orient it, it's going to have the same stiffness in every direction. So it's not like an I-beam where we would have to keep it perfectly aligned vertically. Again, hollow is because we want to keep the weight down as much as possible. And we've already decided we want to make it out of steel rather than wood. It's pretty easy to find. It's strong, stiff, and really not too expensive either. So with those decisions already made, those assumptions, really all we have to do is decide what outer diameter and inner diameter we want this bar to have. Now, when you get into mechanics and materials, you'll learn how to calculate the deflection of that beam, and it comes up with this equation here. So W being the load, the 500 pounds, got the length, which we want to be in inches, 120, and the modulus of elasticity. How stiff is the material? Well, for steel, we'll use a modulus of elasticity of 30 million psi. So the only other things in there, of course, are the outer diameter and the inner diameter. Now, the deflection equation, we can write it this way. Since we know it has to be less than or equal to 1 inch, then we'll show this. The calculated deflection less than or equal to 1 inch. And again, there are a lot of values of big D and little d that'll satisfy that. And again, we could select the inner diameter arbitrarily, find the d that make the equation true. But again, we're trying to find the best solution. And in this case, probably what we want to do is to minimize the weight. And so we can do that, of course, by just minimizing the volume of the steel in the beam. And it's also going to make it easier to install. Maybe a couple of guys can do it by hand rather than having to get a crane, etc. So we want to make this as light as possible, which will also, if we're definitely using steel, it'll make it as least expensive as possible as well. So the equation for volume is just, well, it's the volume of a hollow cylinder. So the length and the diameters come into play there. Now, a couple other things we might want to say. If we just try to optimize that, we might end up with something that's 3 feet in diameter and 1/1000th of an inch thick, something like that, a very unreasonable kind of thing. And so we want the wall thickness. We're going to add a constraint. We're going to say, okay, we want the wall thickness to be at least 1/8 of an inch thick. So the difference in the diameters divided by 2, greater than or equal to 1/8 of an inch. And a couple of things we may not know, but if we try to, again, do the mathematical optimization, it could end up being that we have negative values of d or d. So mathematically, that might be good, but of course, physically, we can't have that. So we might add a couple more constraints that both the outer and inner diameter have to be greater than or equal to 0. Okay. Now we can state now our optimization problem, and when we use Excel Solver in just a little bit, we kind of set it up this way. what do we want to do? We want to minimize what we call our objective function. We want to minimize the volume. We're going to do it by changing our inputs, capital D and little d, and subject to what we call these constraints. Again, they're constraints on our problem in that whatever we pick, the deflection has to be less than or equal to 1 inch, our thickness has to be greater than or equal to 1/8 of an inch, and both the diameters have to be positive values. So that's how we would set up this problem. Now you notice there's nonlinear equations within this, and so we would call this a nonlinear constrained optimization problem. Now there are a couple other ones that we're going to look at kind of in order. We're going to start out by looking in the next video at unconstrained nonlinear problems. So in that case, there's no limitations being put on the variables, and so again, no constraint equations there. Then we'll look at problems that are constrained, but the equations are all linear. And the reason for looking at that is that there are certain solution methods that apply to these kind of equations if they're all linear. And finally, like the problem we just looked at, we'll look at nonlinear constrained equations. And what that means is either the objective function or one or more of the constraint equations are nonlinear, then it falls into this category of nonlinear constrained. Again, just like the beam problem we just looked at, which we will solve a little bit later on. So with that in mind, as said, the next one we're going to look at, we'll look at some tools for solving nonlinear unconstrained problems.